In this octave lesson, we will go over for loops and some example problems that we might see in Octave. Alright, so our first example is to try to predict the output of this snippet of Octave code. So let's type it in. Alright, so the for loop will go in 4 steps. I will go from 1 to 4, and after it runs, we'll display the value of A. Display is the same as DISP, except I believe it gives an extra line at the end. Alright, so let's try to execute this. You'll do it slightly differently in your own Octave version, but this is on an Apple computer using the command line. Alright, so it says the answer is 20. So let's see what's going on here. So I have the Octave shell open right here. Start out A equals 0. Now let's run through this for loop one at a time by hand. So let's let x equal 1. Then we're going to say A equals A plus 2 times x. So you see now A is equal to 2. The new value of A, which is 2, is equal to the old value of A, which was 1, plus 2 times the current value of x, which is 1. So 0 plus 2 times 1 is 2. Now we're storing the value A2 in A. So let's let x now go to 2. And let's run the same command again. A equals A plus 2x. 6. The new value of A is the old value of A, which is 2, plus 2 times x. X is still 1, so 2 plus 2. So A is equal to 2, the old value of A, plus 2 times x, which is now 2. 2 times 2 is 4, plus 2 gives us 6. Next, the for loop will say x is 3, and it'll do this step again. So let's do this step again. A equals A plus 2x. Now A is 12. And one more time, x is now equal to 4, the final value for the for loop, 1 to 4. And now let's execute this line here. And we see A is equal to 20. Alright, so that's problem number 1. Let's see if there's another interesting for loop to try out. So let's try problem 1.8. Let's write a for loop to compute this sum. Alright, so let's see. Alright, so remember, computers can only add 2 numbers at a time. We can't add 19 numbers in one shot. So let S equals 0. And that will represent the sum, a running sum. Alright, so we need a for loop for I equals 1, 2, well, not 1, maybe 2 to 20. Because we want to start at 2 and end at 20. And we'll simply say that the new value of s is the old value of s plus, well, as I changes from 2 to 20, it should add each time this last number. So how about 1.0 divided by I raised to the second value. Now I won't put a semicolon just so that we can see what happens, but you probably would want to usually. And 4, and let's display the final value of s. Alright, so let's execute this code. And it looks pretty good. Why did I put 1.0 here? Well, that's not necessary. See, 1 over 2 is a half. But in some computer languages, if you say 1 over 2, the answer would be 0, because it would use division as integers, and it would give you a remainder if you called for it. So just to be on the safe side, I like to convert things to decimals and do things like that. But in Octave, it's not necessary. But in other computer languages, it is necessary. For example, I believe in Python, well, I guess Python works too. If you want to do the division like that you do in elementary school, you need 2 bars. So I don't think that works here, but let's check. No, it doesn't. Octave doesn't do that. You need to use a different command for that. All right, let's quit out of Python. Okay. All right. So there's actually a nice way to do this that's even quicker. So let me show you. So if we say something like x equals 2 to 20, we get a whole list of 20 numbers, right? Okay. Now what we could do is we could say 1 over x squared. Now we're going to get an error here, but I just wanted to show you that. It says use the dot caret. So instead of saying 1 over x squared like this, you need the dot caret. So I should point something out. I should point something out that when I did things like 2 to the 3rd power, I think in class we learned it this way, but it's the same thing. So in some computer languages, you use the double star to do exponents. In Octave, you can do either one. Okay, all right, so take a look what we did here. So once again, let's start over. So x are the numbers from 2 to 20. And then what I did is I said, take 1 over x squared. But see this extra periods here? That is so that the division works on each number, and this period is so that the square works on each number also. So if we do this, and in fact we can store this, let's call it y, as if you were going to graph it. Okay. Now, what we basically want to do is take the sum of these numbers, right? So you could just say sum of y. If you want to see more decimals, there they are. All right. This is a nice little exercise to try out and see what answer you get. So you might want to pause this video for a minute and see. The answer is 34. Just follow the logic along. You can do it step by step. Maybe we should. So A is 5, B is 3, B is 3, B equals A plus B, A equals A plus B, B equals B, B equals B plus A equals B plus A. So it's the left side that counts. The left side is what becomes stored. That's the variable that gets updated. The right side do not. How would we write a program to calculate the derivative? Well, that's a bit more complicated, but let's give it a try. So let's start out with a lot of decimal points. So we'll go to format long. Let's define a function. I'll just copy and paste it right from these problems. And let's say our function is x to the 5th power. Okay? And suppose we want to find the derivative when x is equal to 1. So our goal is to find f prime of 1. Alright, so we want to use the formula f of x plus h minus f of x. We need another parentheses here because we want to divide the whole thing by h. And let's call this quantity d for derivative. Well, we need to say what x is and what h is, right? Let x equal 1. Now, we need to say what h is, and we want h to get smaller and smaller. So let's do a little for loop here. For I equals 1 to 10, let's put a line here before. Let's start out h is equal to 0.1. Alright, so we'll get our first answer. Let's display D. Now we have to make h a little smaller, right? So let's let h equal the old value of h divided by 2. That will have h each time, and then it'll get plugged back into the derivative formula, and we'll have a derivative, n4. And then let's display the final value is let's put some carets there for good measure. Display D. That's what we're after. All right, let's try to execute this program and see what happens. All right, well, that looks reasonable, right? We're getting close. Let's see if we can be a little more accurate, right? So how about 1 to 20 maybe? Let's make h get smaller. There we go. We have 5 zeros. Let's see how accurate this baby goes, right? How about 30? Seems to be a limit, right? No pun intended there. So, seems to be a limit to the accuracy. Now there are ways to have really, really accurate computations using various libraries. One example is a library in Python. I believe it's called NPMath. And you can have thousands and thousands of digits until you run out of computer memory, basically. But that's not necessary here. Let's say we want so let's go back to something reasonable like 25. Save it. All right, that's pretty good. That looks like about as good as we're going to get in Octave. And in fact, if we want the derivative at another point, how about x equals 2? 80. And you could check that this works, right? F prime of x is equal to 5x to the 4th power. And if you plug in x is equal to 2, you'll get the answer is 80, exactly 80. 5 times 16. So we got pretty close with our derivative formula. All right. So to conclude this Octave video, let's try something a little bit different. Let's take a look at a nested loop. This is a double loop. Now, this particular loop is a bit long to go over by hand, but let's simplify it in a few minutes. All right, so let me fix it. Alright, I think it's okay now. Let me try to execute it. Alright, looks like we're okay. 1.036. A little more accurate. Alright. Now what's going on here? Well, there's two loops here. An I loop and a J loop. But in total, it's run 100 times. So these three lines are run 100 times. Now, in order to understand this a little more, let's simplify the problem. And let's just do it 2 times each. Alright, so what went on here? So let's clear the memory. Clear. Format long. M equals 1. N equals 2. X equals 0. Okay. Now I is 1. Starts at 1. We're right here on this for loop. Okay, so I is 1. Now J is 1. X equals X plus 1 over N. Okay. N equals N plus M. So far so good. M equals N plus 3. Okay, now we just ended this line here, and currently I is 1 and J is 1, as you can see. And now the next step is to go back here and let J go to 2, but I stays at 1. We're still in this first iteration. We won't update I to 2 until we finish going through this entire for loop, however many times we have to. When that's done, we get to here, and then we jump back to there and start J back again at 1. Alright, so now J is 2. Remember, we're keeping I at 1. Now we have to repeat these 3 lines. In fact, I could do them easier. Well, let me do them slowly. Alright, X equals X plus 1 over N. N equals N plus M. M equals N plus 3. Okay, J was 2. We just iterated the loop. We're done. So since we finished the complete inner for loop, we now jump back to I and let I equal 2. So now we're back to the outer loop. I is 2. Now we have to do this inner loop twice again. J equals 1, J equals 2. So go back and set J equals to 1. And let's do these 3 lines again. Whoops. That didn't work out too good. Try it again. Alright, let me do it by hand. Alright. X equals X plus 1 over N. N equals N plus M. Actually, I meant to have, no, too late now. M equals N plus 3. I wanted to show you the results each time. So let me show you X's and N. Okay. Finally, we will let J equal 2. And we will repeat these 3 lines. X equals X plus 1 over N. N equals N plus M. n equals n plus 3. Okay, j was 2, I is 2. That's so when j is 2, we get to here. We go, I is 2, then we're done. So we finish and display x. And that's the answer. So that's an example of a nested for loop.